So today we're going to be looking at relative extrema. And the whole idea of what are relative extrema is they are the peaks and the troughs. They are the top of the hill and the bottom of the valley on a graph. And we're going to be taking a look at their critical values and seeing what they look like through the first derivative. You're going to see the reference of critical values when in reference to relative extrema, because there is something that we're going to have to find as generally important points on graphs, usually in reference to either the maximum profit or the minimum loss or the maximum height and altitude. They're important points, which is hence critical value. So let's take a look at a few of these problems. So let's start out with number one. So now number one, we have this graph of f of x equals x squared divided by x squared plus 4, which gives us this generalized shape. And we want to find the value of the relative extrema, or the critical value at 0, 0. So I want to find out what is the value of the derivative at this point on the graph. So my first thought is, let's make sure that on that part of the graph, I can actually find the derivative. So we do that just by taking a quick look and saying, are there any holes in the graph? I can draw a tangent line. Are there any sort of removable points? And the only removable point that we could have is if x squared plus 4 equaled 0, which would be x squared equals negative 4. So I know that it can't exist in the complex plane because there's two parts in the complex plane where the square root of x would not be equal to plus or minus 2i. So we're not too concerned about that because it looks like we're just dealing with the real plane. But the lateral plane, we might run into a few problems. So let's go ahead and jump into this. Let's find the derivative of this equation. Well, I know the derivative of this equation, let's do this in blue, is going to be a u over v derivative. The u, what we're seeing right here, is going to be my x squared, and my v is going to be my x squared plus 4. So u prime is 2x, and v prime is also 2x, the 4 going away. And I know with a u over v derivative, what I'm going to do is I'm going to do low d high minus high d low all over low squared. So I have low, which is my v. Let's do v low d high minus high d low all over low squared. So we've got this going on. Let's fill in these things. So low is x squared plus 4. D high is 2x minus high d low all over low squared. So x squared plus 4 squared. Let's simplify what we can on this. So this is going to leave us with 2x cubed plus 8x minus, 2x cubed. Awesome. This is going to all be over. That's going to end up being x to the 4th. We're going to go ahead and double this. So that's a 4x squared. That's going to be an 8x squared, and then plus 16. A couple things jump out right off the bat. My 2x cubed minus 2x cubed are going to cancel out, and I'm left with this value. So 8x over x4 plus 8x squared plus 16. Awesome. And so now all I need to do, if this is the derivative, let's go ahead and recenter that. If this is the derivative right here, so this is f prime of x, what is the value of f prime of x at 0, 0? Well, I only have one variable that I can plug in, and that's x. So let's go ahead and plug in x value. So f prime of 0. So that's going to be an 8 all over 4 plus 8 squared plus 16. So I plug in a 0 into all three of these. I notice right off the bat, cancels, cancels, cancels. So I'm left with the f prime of 0 do it in red, is 0 divided by 16, which is just going to be 0. Awesome. So that means that the tangent line at this relative extrema is a flat line. There's no slope. The slope is going to be 0. So let's take a peek at another one, number 3. So number 3, we've got this graph. G of x is equal to x plus 4 over x squared, which looks like this thing right here. And I want to find the value at 2, 3. So the first thing we're going to do is I'm going to make sure that, yeah, it doesn't look like there's any holes. It looks like the only way I can do that is by drawing a straight line through it. There's no weird things. So let's go ahead and jump straight into this. And so the first thing I'm going to do is I'm going to rewrite this as a polynomial with all exponents in the top. I'm sure there's a way to describe that. Boom. And there we go. So our first step is if we want to find the derivative, let's see, we did the last one in blue, so let's stick to it. So g prime of x is equal to, not an x, it's going to move the power, so it's going to be a 1. Let's see, minus 8x to the negative 3. So I'm going to get g prime of x is equal to 1 minus 8 over x cubed. And I want to find out where it at 2, 3. So I'm going to go ahead, if that is the derivative, I'm going to say g prime of 2 for my x value. Plug in my 2. Now at this point, I'm just going to go ahead and evaluate it. So 1 minus, let's see, 2 cubed is 8, so 1 minus 8 over 8, 1 minus 1, which is 0. So my g prime of 2, again, is 0. Okay, so it seems like we've got a common theme. The value at a relative extrema in the first one and in the second one were both 0. So what I want you to try is I want you to try number 5, pause the video, unpause it when you're done, and see how well you did. Okay. So now that you've given it a shot, what your first thing that you should have looked at is you should have said, hey, I have an f of x, and I'm trying to find the value of this relative extrema. First off, this is a graph that comes to a point, which means that I cannot find the derivative at this point because the tangent line can exist in any one of these orientations because it's through a point. So there is no one tangent line. There's an infinite amount. It can be any one of these angles. So it does not exist. So I know that, let's put this, f prime of x does not exist at negative 2, 0. So visually, I can see that. But what happens if we don't have the graph and we don't have time to graph that? Can we prove that mathematically on number 5? Well, let's take a look. So this looks like a chain rule one that we can easily solve. I can't do this, but I can say if u was equal to x plus 2, well then my new function would be u to the 2/3. I can find the derivative of that easily. So f prime of u is going to be 2/3 u to the negative 1/3, or 2 over 3 cube root of u. Now that's not rationalized, but we're not too worried about that because we're going to evaluate and see what the total value is, so I'm not worried about plugging that into a rational form. U prime is going to be 1. So if I want to figure out, let's separate this a little bit. So f prime of u prime is 2, 3 cube root of x plus 2 times u prime, which is times 1. Awesome. So Here we go. We're going to plug in a -2 and see what we get. So f prime of -2 is equal to 2 times 1 up top is 2. Actually, let's just go ahead and half box that up because that's what we've been doing with the derivatives. So that shows that is the derivative. Is 3 cube root of -2 plus 2. And here's where we see where things fall apart. -2 plus 2 is 0. The cube root of 0 is 0. 0 times 3 is 0, which means this is equivalent to 2 over 0. Or we could say that f prime of -2 does not exist at -2 comma 0 because it is undefined. Awesome. So that brings us to the second part, which is instead of finding the value of the derivative at a point, we're going to be finding which points make that a local maxima or minima, which in essence mean we're going to finding the critical values by setting the derivative equal to 0 and solving. Now, this can be some of the most tough and some of the most challenging style questions because you're going to have to figure out how to set these functions and how to set these equations equal to 0. But don't worry, just press through and you'll start to recognize a lot of the patterns and a lot of the sequences of which will be popping up in the future. So let's jump into it. Number 7, the first one. Pretty straightforward. This is a quadratic, so I know that because it's positive, I should have 1 at the bottom or at the vertex. But really all we need to do is say, okay, the derivative is set equal to 8x minus 6. There is my derivative. I'm going to set this equal to 0 and solve, which means 8x is equal to 6, or x is equal to 6/8, or x is equal to 3/4. Boom. Easy enough. Now, let's try one more. A little more challenging. This one, we have a u times v function, which means I'm going to have to set u is equal to t, so u prime is 1. V is equal to the square root of 4 minus t, which means v prime, we're going to have to come over here and do a subroutine. So this would be easy if this was the square root of u. So I'm just going to go ahead and set u equal to 4 minus t. So u prime is equal to negative t. So my function with u in it is going to be the square root of u. So my derivative is going to be, let's see, that's to the power of 1/2. So 1/2, or 1 over 2, 1/2 subtract 1, negative 1/2, square root of u on bottom. So let's go ahead and take f prime of u, plug in our u, and multiply it times u prime. So negative t, we're going to plug this in, so times 1 over 2 square root of 4 minus t. That we're going to plug in here. So it's times 1, so it's just going to be a negative t all over 2 square root of 4 minus t. That's a t up there as well. Perfect. And so now we need to find the derivative. We're going to do our little cross. So vu prime, so times 1, so it's going to be the square root of 4 minus t is equal to the product of these two. So I'm going to multiply these two together. So, no, not equals, it's going to be plus. So negative t times t is going to be negative t squared all over 2 square root of 4 minus t. This is the derivative. We're going to set this equal to 0 and solve. So the easiest thing that we could do is we could just go ahead and say, let's add this over to the other side, and that way I have a square root on each side. And before we even continue further, I'm going to expand this just a little bit because we're going to be using up a little more real estate. So I have the square root of 4 minus t is equal to t squared all over 2 square root of 4 minus t. Awesome. So now that I've added that to the other side, I can go ahead and I can multiply both sides. Or I guess you'd say, yeah, cross multiply both sides by this denominator over here, which means I'll have 2, 4 minus t is equal to t squared. Distribute this, 8 minus 2t is equal to t squared. Move everything over to one side, 0 equals t squared plus 2t minus 8. At this point, it's just a quadratic. I'm looking for what factors of 8 make a difference of 2. That's going to be a t plus 4 and a t minus 2. So I get t is equal to negative 4 and t is equal to 2. Now, of these two values, I'm only looking for the values where t is less than 3. So if we look at the whole problem from start to finish, t is less than 3. It's going to be t is equal to 2, and t is equal to negative 4. Awesome. So let's move on to number 11. So now that you've seen some of the tricks, and it's really not too bad, go ahead and give number 11 a shot and see how well you do. Pause it, unpause the video when you're done, and see how well you did. Okay. So now that you've had a shot, we know we're looking for values between 0 and 2 pi. So I'm only looking for the first iteration of the unit circle. So I'm going to take the derivative, which in this case is going to be h prime. Okay. This would be easier if this was a chain rule. So I'm going to say, okay, let's let u equal sine of x, which means u prime is going to be the cosine of x. And my function is u squared, which means the derivative of that function is going to be 2u. So I'm going to say it's going to be 2 times the sine of x times the cosine of x. The cosine of x is just going to be negative sine of x. I'm going to take this, my derivative, and set that equal to 0. So 2 sine x cos x minus sine x is equal to 0. Well, similar to a quadratic, I'm going to factor out a sine x. 2 cos x minus 1 is equal to 0. So now I have two separate equations that I can solve for, or two possible values, sine and cosine, meaning there might be more than 2. So sine x is equal to 0. And the only time sine is equal to 0 when the y value is equal to 0 is going to be at 0, 180, or 360. Now, I can't assume the 0 and the 360 because I can't assume the extremes of the circle, but I can assume 180, which means x is going to be equal to pi in that one. For this one, for 2 cos x minus 1 is equal to 0. That's 2 cos x is equal to 1, and cos x is equal to 1/2. Whenever cosine is equal to x, or cosine of x is equal to 1/2, that is going to be one of my special triangles. So whatever angle that is, the cosine, which is adjacent over hypotenuse, is going to be 1/2 over 1, or I could look at it as 1 over 2. Actually, let's give a little more room and let's redraw that. So the cosine of whatever angle is 1 over 2, which is 1, 2 squared of 3. That is a 30, 60, 90 triangle. Not necessarily drawn to scale, but get the idea. So that means it's either going to be a positive 60 or a negative 60. Those are the only times cosine is positive. If it was on the other side, it'd be negative. So if I'm looking between 0 and 2 pi, I have x is equal to 60 degrees, which is pi over 3, or 300 degrees, which is 5 pi over 3. There we go. Okay. Number 13. Again, we're looking at a u times v problem. So if I have a u times v, my u is going to be t, so u prime is 1. V is e to the negative 2t, which means v prime, I'm going to have to come over here and do a subroutine, which isn't going to affect it too terribly much. So if negative 2t was the u, negative 2t, u prime is negative 2. F of u is e to the u. F prime of u is e to the u. So that would mean e to the negative 2t times u prime, which is negative 2. We get that, which is going to come over here and do that thing. Let's go ahead and cross those. So vu prime is going to be e to the negative 2t plus uv prime. So t negative 2 e to the negative 2t. That is my derivative, and I'm setting that equal to 0, and I'm solving. Just like before with my sine and cosine, I can factor out a sine function. Here I'm going to factor out an e to the negative 2t. So e to the negative 2t is going to be factored out of 1 minus 2t, which means I have two values that I'm going to set equal to 0. So again, I'm going to bust out a little extra paper here, just to give us some more room to work with. Let's zoom out just a tad. There we go. So I know that with this, e to the negative 2t must be equal to 0, and I know 1 minus 2t must be set equal to 0. This isn't too bad. There's my first value. The second value, no matter what I set this equal to, e, no power of e is going to make that equal to a 0, so I know that this does not exist. The only value for my t is going to be 1/2. Awesome. Okay. And so by far one of the most challenging ones that I want you to give a shot is number 15. So go ahead, take a shot at number 15, pause the video, unpause it when you're done, and see how well you did. Okay. Let's take a look at how it's going. Kind of have like a chain within a chain. So u, v, u is going to be x squared, which means u prime is 2x. V is the log of 2x squared plus 1. We already see where this is going. I can't take the log of something. So I'm going to come over here and say v prime is equal to subroutine. If that was a u, so that's x squared plus 1, u prime would be 2x. My f of u would be log 2 of u, which the derivative of a log is going to be f prime of u is going to be 1 over the natural log of the base, so ln of 2 times whatever this thing is, so times u. So let's this up. So if I'm multiplying by u prime, that 2x is going to be up top. Natural log of 2 times u, which is times x squared plus 1. That's all going in right there. Set up our cross, vu prime. So 2x log base 2 of x squared plus 1 times this, or not times this, plus, let's see, x squared times 2x, so x squared times 2x, all over the natural log of 2 times x squared plus 1. Here's my derivative. I'm going to set that equal to 0 and solve. And so one of the first things you see that jumps out at you again is that I have a 2x and a 2x. The first thing I can do is factor out the 2x and say 2x can be equal to 0, which means that x can be equal to 0, and there's my first answer. Kind of fell off the screen there. The second thing that I'm going to be working on is going to be this remaining portion. So I have, let's zoom out just a bit. I have log 2 of x squared plus 1 plus x squared over the natural log of 2 times x squared plus 1. And what we notice right here, this is where the trickiness comes in. There's really not a clean way to solve this, but what we can do is we can check out a graph and see if we're going to get a unique value for this one that hasn't already been covered. So let's take a peek at what that graph would look like. So this is the part of the graph that I want to see. Now I could graph the entire thing if I go over here and I say, okay, x squared times, I can't type in log with different bases in this, so I'm just going to use the change of base rule. So log of x squared plus 1 divided by log of 2. Take a look at the graph. What I notice is that my graph comes nice down right here. I'm going to zoom in on that point just to make sure. Yep. And so I've already got my critical value of 0. So even if I calculated, definitely I got one over here for left bound and over here for right bound. End up with an extremely small decimal, which is, for the most part, going to be just 0. This may or may not be just some sort of rounding error within the calculator. So we can safely assume that we found the one and only unique critical value. And there you go.